Okay, so now we're gonna go over section 4.6, which is modeling with exponential and log functions. Modeling with exponential and log functions. Okay, I'm gonna change this is too light, so let's try blue. Okay. So in this section, we're gonna see some applications of log and exponential functions. There's different kinds of applications. There's exponential growth and decay. There's Newton's law of cooling. So we're gonna go over those, and you will be given the formulas on the test. So let's start with exponential growth and decay, which is doubling the time. Exponential growth is doubling the time, and then when we do decay, we talk about half-life. So the formula we use is n of t equals n sub 0 times 2 to the t over a. Let's explain every one of those. N of t is the population size at time t. So we know population sizes grow exponentially unless there is war or famine. N sub 0 is the initial population size. It's the size of the population at t equals 0. And then a is the doubling time. So how much time do we need to double the population, and t is the time. These t and a, as you can see, they have to have the same unit of time. So if t is in years, a has to be in years. T is in month, a has to be in month. Let me just, there's an example that I put in the notes. Let me explain that so you can understand where this formula came from. Okay, so it's not just a formula, it makes a lot of sense. So suppose you invest $1 in an account. I just made it simple, just $1, okay? That promises to double your money every month. So if you start with $1, a month later it's $2, 2 months later it's $4, 3 months later it's $8, and so on. So here's a chart, time, and then n of t, which is the amount. Remember, n of t, that instead of population size, now it's the amount of money that you have at time t. So in 1 month, that dollar would have been $2. In 2 months, it's $4, which is 2 square. 2 to the 1, 2 to the 2. In 3 months, it's $8, which is 2 cubed. You can see that. And in t month, it's gonna be 2 to the t. Okay, so n of t equals 1, which is what you started with, times 2 to the t. Now, if we start with $100, then n of t is going to be 100 times 2 to the t. That's your n sub 0, initialized population, in this case, initial amount of money you put in. Also, if money doubles, you see, we have it as money doubles every month. If money, say, doubles every 3 months, money doubles every 3 months, then the formula is going to be n of t is 100 times 2 to the t over 3, and that's a, that we refer as a. Okay, and this is your n sub 0. So that's where this formula came from. Okay. So let's see an example about that. Number 4, page 378. It says a certain species of bird was introduced in a certain county 25 years ago. Biologists observe that the population doubles every 10 years. Population doubles every 10 years. And now the population now is 13,000. What was the initial size of the bird population? So that we want n sub 0, the initial size. Well, if we're using the formula n of t equals n sub 0 times 2 to the t over a, n sub 0 is what we need to find. T, so t is, see, we know a is 10, but what is t? Let's read to make sure we know what t is. So a certain species of bird was introduced in a certain county 25 years ago. So 25 years have went by, and then what's the population? 13,000. Okay, now it's 13,000. So 25 years has went. So what was that population 25 years ago, which is the initial population? So to solve n sub 0, we divide by 13,000 over 2 to the 2.5, which is roughly 2298. So that was the population size 25 years ago. Part B, estimate the bird population 5 years from now. So now we have the formula n of t equals 2298 times 2 to the t over, what's the doubling? 10. So 5 years from now, so n of t equals 2298 times 2 to the 30 over 10. Right? 5 years from now, that means t is 30 years. Okay, because it started 25 years ago. So if you put that in our calculators, it's 18,384 birds. And part C, sketch a graph of the part. Sketch a graph, so use your grapher. You can do that yourself. Okay. Alright, so there's a handout about exponential growth and exponential growth. So there's two formulas, one for the doubling time that we did, and one where you have its relative growth rate, which is like a equals PERT, which is I'm going to talk about right now. Okay, so let me write this down. Exponential growth, and this one deals, instead of doubling time, it deals with relative growth time. And you will be told which one to use on the test, okay? N of t equals n sub 0 e RT, which is similar to A equals PERT, if you remember that, okay? It's very similar, it's just different notation. N of t is the population size at time t, same as before. N0 is the initial size of the population. R is the relative rate of growth, which is expressed as a proportion of the population. Relative rate of growth expressed as a proportion of the population, and t as time. So there's no doubling time, okay? It's the rate of growth, okay? In terms of money, it's the interest rate, okay? So for that, to explain that, let's look at page 379. The population of a certain species of fish has a relative growth rate, so you can see why you have to use that formula. of 1.2% per year. It's estimated that population in 2010 was 12 million. Population 12 million in 2010, and R is 1.2%. Find an exponential model for the population T years after 2010. So they want, so basically they want to find n sub 0, and we want to know R, and then we'll have that formula. We have, so at t equals 0, the population is 12 million. I'll just put 12 and then say this is in millions, and then e to the 0.012t. That's in millions, okay? Part B, estimate the fish population in the year 2015. Year 2015, so it's 5 years from 2010, so t is 5. So n of 5 is 12 e to the 0.012 times 5. So let me put it in my calculator. 12 and then e to the 0.02 times 5. So the population size in the year 2015 is 12.742, and remember this is in millions, okay? And then part C, after how many years will the fish population reach 14 million? So we want t when n of t is 14 millions. So we have the formula, we'll just use it right there. 14 equals 12 e to the 0.012t, and so you can see now we're solving an exponential equation, which we went over last section. So we want to isolate the e, dividing by 12. 14 over 12 is 7 over 6, and then since the base is e, we ln both sides. So that's going to be 0.12t is ln of 7 over 6. ln of 7 over 6 divided by 0.012. So ln of 7 over 6 divided by 0.012. It's 12.846. So 12.86, 12.85 years. And then D, you do your grapher. Okay. So the third application of exponential and log equations is radioactive decay. Radioactive decay. Radioactive decay. Okay, so the formula for radioactive decay is m of t equals m sub 0 times e, and you notice the negative there because of decay. So you have a negative exponent, meaning you're going to have an exponential decay. So m sub 0 is the initial mass, and usually it's in grams. Initial mass of a radioactive substance, whether it's uranium or iridium, a radioactive substance. And we know that radioactive substance decay over time. That's why they're so dangerous. M of E, it's the mass of that radioactive substance remaining. Because what decays, we're interested in what remains. Math remaining at time t. So sometimes they can trick you and tell you how much was decayed. So you're going to figure out what's remaining percentage wise. If 60% decayed, that means 40% remains. Keep that in mind. R, instead of rate of growth, rate of decay of the substance, radioactive substance. And t, of course, is the time. And remember, in exponential growth, we talked about doubling time. In radioactive decay, we talk about half time. And when we say half time, the half time of a radioactive substance the half-time of a radioactive substance is the time needed. So it's a time period. Which time period? For 1/2, just like it says half-time, of the original amount. So if you have 10 grams, how much time does it take to make in 10 grams? Original amount of the substance to decay, of the substance to decay. So if you're starting with 20 grams of uranium, how much time? That's the half-life. How much time is going to go by for the 20 to become 10 grams? Whatever time period that is, that's called the half-life. It could be 10 years, 10,000 years, 5 years, we don't know. Okay? So instead of doubling time, it's half-time or half-life. And the formula for the half-life, for finding half-life, H, we'll use H for half-life, it's ln of 2 over R, where R is the rate of decay, okay? Where is the rate of decay? You know, R is the rate of decay. Also, you know the formula m of t equals m sub 0 e to the negative RT can also be written as m of t equals m sub 0 2 to the negative t over h. Just like, if you recall, we had exponential growth, one for R and one for A. You can see right there, n of t equals n0 2 to the t over a, no negative because it's growth, and then n0 e to the rt. We have two formulas for exponential decay, one with rt and one with t over h, depending on what you're given. You can use either one of them, but it really depends on which one is easier for you. So 18, page 380. Let's look at 18, page 380. The half-life of cesium-137 is 30 years. So every 30 years, half of the initial amount decays, half remains. Suppose we have a 10-gram sample. So if we're using m of t, m sub 0 is 10 grams, the initial amount. Find a function m of t equals m sub 0 times 2 to the negative t over h. So they want us to use the half-life formula, obviously, that models the mass remaining after time years. So m of t equals m0 is 10, and then h is 30. Okay, and that's all they want. Part A. Part B, find a function m of t. So they want now in terms of the rate of decay minus rt. Okay, remember we know that h equals ln of t over r, or r equals ln of t over h, 2 over h. So r equals ln of 2 over 30. So roughly ln of 2 divided by 30, it's 0.023105. You want to carry as many decimal places as possible to get an accurate result eventually. So m of 10 is the m0, 2 to the minus r, which is 0.023105 t. Okay, part C, how much of the sample will remain after 80 years? Now you could use either formula, but I'm going to do A because this is more accurate. This is an F. Okay, I rounded off. So how much of the sample would remain after 80 years? So what's M80? It's 10 times 2 to the negative 80 over 30, which is 8 over 3. We can cancel out the zeros. So 10 times 2 to the power negative 8 over 3. And we started out with 10 grams. After 80 years, it would be about 1.6 grams. It depends on how many decimal places you want. I just rounded off to 1. I mean, you could do 3 or 4 like I did in the notes. Part D. After how many years will only 2 grams of the sample remain? After how many years? So obviously they want T will only 2 grams remain. Remember, we're always interested in what remains. If they had said, oh, when 2 grams decay, that means 8 grams remain, right? Because started with 10, but give us the remaining. That's what we're gonna put in the formula. Now again, we could do either formula, so I'll just use the exact one. M of t equals 10 to the negative t over 30. We want to find t. M of t is 2 grams. T over 30, divide the 10. That over 5 is 2. And now it's an exponential to the base 2, so we're going to do log base 2. Log base 2. We have calculators. It is hard when we have calculators. Is log base 2 of 1 over 5th. We're going to times by negative 30 to get rid of the fraction. So t is negative 30 times log base 2 of 1 over 5th. And we're going to put in our calculators. So negative 30 times log base, so we're going to go to math and then go up to log base 2 of 1 over 5. And in about 69.66 years, that would happen. Okay, let's look at number 24. Number 24 from page 380. Okay. It says carbon 14 dating. The burial cloth of an Egyptian mummy is estimated to contain, so they found the burial cloth of an Egyptian mummy and they found that it contains 59% of C14. That's what they use to estimate how old a mummy is, or how old is a whatever they find that's thousands of years old. Okay. How long ago was the mummy buried? How long ago? So they want to know the time. The half-life of C14 is, we needed that, so we have that 5,730 years. That's the half-life for C14. So since it's about half-life, we're going to use the formula for that. M of t is m sub 0 2 to the negative t over h. So 59% of the initial amount of C14 remain. So basically, if they had 100 grams initially, what remain? Remember, we're always interested in what remains. Of t is what remains, not what decayed. So they give us what remains, which is good. So if you start with 100 grams, then 59 grams remain. Okay, if you divide 100, you get 0.59. If you divide with 200, so you can put in any number here. You take 59% and put it there, because 59% of the initial amount remains. Okay, t over and h is 5730. Now, you might be wondering, why did you put 100? Why don't you put 200? Well, no matter what you do, look, if you divide the 100, it's 0.59 equals 2 to the negative t or over that. Let's say you did 500. So what's 59% of 500? Let's do that. 0.59 times 500. That's what remains is 295. So if you divide by 500, you're still gonna get 0.59. So m sub 0, this is 0.59 m sub 0, so you're gonna cancel it out and you get 0.59. Okay, so that's why you can put in any number, put an easy number like 100, because 59% of that is 59. So it's a log equation. The base is 2, so we're gonna do log base 2, log base 2. So negative t over 5730 equals log 2 of 0.59. So log 2 of 0.59, we're going to times this by negative 5730 to get rid of the fraction. Negative 5730 times log base 2 equals that. We're going to put that in our calculators. So negative 5730 times, we're going to do log base, so math up to log base 2 of 0.59, and that it's about 4362 years old. Okay, that's how old that mommy is. Alright, the last application that I'm going to talk about is Newton's law of cooling. Newton's law of cooling. Let me explain that. The rate at which an object cools is directly proportional at which an object cools. So if you have a pot in the stove or whatever you're cooking, and then it's done, and then you take it out, it's too hot, and then it starts cooling until it takes there's an equilibrium between the temperature of the pot and the room temperature. Okay, so that which an object cools, that pot, is directly proportional to the temperature difference between the object, the pot, the object, and its surrounding. Could be the room temperature. Okay, its surrounding. Provided that the temperature difference is not too large. Is not too large. So the temperature at which an object cools down, T of t, temperature at time t, is Ts plus d sub 0 e to the negative kt. So this is the formula we use for Newton's law of cooling. D sub 0 is the initial temperature. Initial temperature difference between an object temperature and its surrounding. Ts is the temperature of surrounding at time t, and t is the time, obviously, and T of t is the temperature of the object and at time t, in this case the pot, and K is the positive constant and it depends on the type of the object. Depends. You don't have to worry about what objects we're talking about. This is physics. On the type of the object. So let's see an example about that. 26 from page 380. 26. Okay, Newton's law of cooling is used in homicide investigations to determine the time of death. The normal body temperature is 98.6 degrees Fahrenheit. Normal body temperature is 98.6 degrees Fahrenheit. Immediately following death, the body begins to cool. It has been determined experimentally that the constant in the Newton's law of cooling is, so we're given that, we don't have to worry about finding it for this problem. Assuming that time is measured in hours, so time is in hours. Suppose that the temperature of the surrounding is 60 degrees, so Ts is 60 degrees Fahrenheit. Find a function t of t that models the temperature t hours after death. We know the formula t of t is Ts plus d sub 0 e to the negative kt. We have k, we have d sub 0, and we have Ts. We'll put them all in there. T of t is, Ts is 60. Initial, see, remember d sub 0, in case you forgot, it's the initial temperature difference between the object temperature and its surrounding. The object temperature, room temperature, that's what was the initial one, minus the 98.6, and then minus t, which is 38.6 degrees. Okay, if you're wondering, e to the negative 0.1947t. The 38.6 I got by doing 98.6, which is the temperature of the corpse, of the dead body, minus the temperature of the surrounding. So 98.6 minus 60 is 38.6 degrees. That's where it came from. Okay, in case you're wondering. So we found that formula, part B. If the temperature of the body is now 72 degrees, how long ago was the time of the death? So T of t is 72 degrees. We want to find the time of the death. Okay, how long did it take for the temperature to cool down from 98.6 to 72? Well, there's the formula. T of t equals 60. We know T of